All right, honey, let's go over these two problems. The first one is asking to review the ideal gas law, and the different versions of the gas constant are to calculate the air density at a 1 atmosphere pressure and a temperature of 298 K. So in reviewing the gas constants, there's 8.314. Really, 99% of the time you're going to use either 0.082057, which is atmosphere liters per mole per Kelvin, or 8.314, which is joules per moles Kelvin. And a joule is in when you have meter cubed, or if you're working with pascals, that's a good one to use for pascals, because pascals, 1 atmosphere is 101,325, 101,325 Newton per meter squared. So if you're going to use that one, but that's not, we're using atmospheres here. So let's use a 0.0257. And all we do is use that formula in the ideal gas law of density, which is moles per volume. You can do density in a number of ways. It's a ratio of mass or moles to volume. So we're going to do N over V for moles per volume. And from ideal gas law, we see that N over V equals P over RT. And we're given pressure and the temperature. We have R. Just plug them in. So we get 1 atmosphere divided by 0.08257 divided by 298 gives us 0.04 moles per liter, but they're asking for molecules per milliliter. So to convert the liter to milliliter, well, centimeter cubed, which is the same as a milliliter. So I'm not fond of centimeter cubed. I know it's common in literature, but I prefer milliliters. It's identical. So let's convert to milliliters. So in 1 liter, we have 1,000 milliliters, right? And now let's convert moles to molecules. We use Avogadro's number. So in 1 mole, we have 6.022 times 10 to the 23rd molecules. And we end up getting this huge number, 2.5 times 10 to the 19 molecules per centimeter cubed or per milliliter, however you want to say that. Okay. The next one is these are both worded poorly in my opinion, but I'm just kind of critical. So we don't need, well, they're telling us number 2, show that if the number density of ozone, I mean, who talks that way? High up at 25 kilometers, which we're not going to use 25 kilometers, we just know the pressure is going to be low. If you're up high, we know you're going to have almost no atmosphere going into space. So high up in the air, you have a density of 5 times 10 to the 12th molecules per milliliter, or per centimeter cubed. And the temperature is not going to be this hot, but they're using 220. It's going to be Arctic up there, but they're using 220 because they're just playing with numbers. And a very low, almost no pressure, 0.027 atmosphere. They're asking then what's the mixing ratio or the mole fraction, which is the same thing, of ozone. So be careful. A mixing ratio is a ratio of either the volumes or the moles, or, you ready for this? A ratio of the densities. So we can get the same, it's the same thing. It's all the same thing. Ratio of moles, ratio of volumes, for gases we're talking, or ratio of densities. All give you a mixing ratio. So we want to use, in this case, the density ratios. We've got the density of ozone, they give us that. Let's convert it to our moles per liter, our favorite. So the ozone density is, here we go, 5 times 10 to the 12th. Molecules per centimeter cubed, so let's convert that into moles per liter. So get rid of the molecules divided by Avogadro's in this case. In this many molecules, 6.022 20 to the third, you have 1 mole. And then to convert milliliters, or centimeter cubed, to liters, in 1,000 milliliters, you have 1 liter, and voila, you get 8.3 times 10 to the minus 9 mole per liter. My favorite way of expressing, this is actually concentration. They're calling it density, but I'll do what they're doing, but usually moles per liter is called concentration, but we'll call it density, same thing. Now for air, we know it's very low air pressure, and they're using 220 K for some reason. I know it'll be much colder, but whatever. It's going to be this low air pressure divided by RT. Why is that? Because density, which is N over V, is the same as P over RT, because we know from PV equals nRT, get N over V alone, all right? Divide both sides, in this case, by, divide both sides by volume, and divide both sides by RT, and you're left with N over V equals P over RT, and we've got P over RT. So P over RT gives us this value, 0.027 divided by 0.082057 atmosphere liters per mole per K, divided by 220, gives us 1.5 times 10 to the minus 3. Okay? So now we just need to do our density ratio, which is the same as mole ratio. They're all the same for gases. The gases are nice that way. So here's the ozone concentration divided by, or density as they're calling it, divided by the air density, which is 5.53 times 10 to the minus 6, which is, 10 to the minus 6 means 1 part per million, excuse me. If we're minus 9, it'd be part per billion. So whatever this exponent is, that's your unit here, the millions or billions or thousands or hundreds, whatever it is. That's all. Thanks for watching. Hi.